First, I'd like to thank the organizers for the invitation and for organizing this nice online conference. Today, I'll talk about an ongoing work with Danny Calegari about normal subgroups of big mapping class groups. Here, big mapping class groups refer to those mapping class groups of infinite type surfaces. These are surfaces that are non-compact in a way that's more complicated than just having finite many punctures. In the introductory talk by Marisa Lavin, you can see a lot more examples, but here let me just give you a few examples. So you could have a surface of infinite genus accumulating to one end on the right. You can also have a surface that kind of keeps branching, and you have a Cantor set of ends accumulated by genus. Or you could do the same thing without any genus, and the last surface you can verify it is actually the sphere minus the Cantor set. A big mapping class group is just a mapping class group of a surface of infinite type, defined in the usual way. Here in this talk, to just consider a particular class of surfaces of infinite type. Namely, we start with a surface S of finite type that's either closed or just have one puncture. And then we remove a Cantor subset on the surface S to obtain a surface of infinite type, sigma. And our goal is to understand the algebraic structure of the corresponding big mapping class group. For instance, what are some generating sets? For the ordinary mapping class group corresponding to the finite type surface S, we know it's generated by Dan twists. However, on a big mapping class group, you will only get a countable subgroup this way because there are only countably many simple closed curves. However, the big mapping class group is uncountable, so Dan twists are far from enough in this view. On the other hand, people sometimes consider some non-trivial topology on the mapping class group, big mapping class group, and consider topological generating sets, where you don't just take the algebraic subgroup generated by a set of elements, but you also take the closure corresponding to the topology. And it's a theorem of Patel and Belamis that you can, these Dan twists topologically generate the pure mapping class group in many cases. But throughout this talk, we'll just consider the algebraic structure. So we'll not refer to the topology and treat the big mapping class group as discrete groups. The other question that we try to answer is that what are some normal subgroups of big mapping class groups? This will help us to understand homomorphisms from big mapping class groups to other groups. Here, let me show you two specific normal subgroups that will play an important role in the main results. First, there is a forgetful map from our big mapping class group to the corresponding ordinary mapping class group. So one nice way to think about mapping classes in the big mapping class group is that you think of these really as mapping classes represented by homomorphisms on the surface S, preserving the Cantor set. And the forgetful map forgets the additional information that we are preserving the Cantor set and treat these mapping classes as ordinary mapping classes. This map gives a surjective homomorphism, and we denote the kernel by adding a subscript naught. This kernel gives us a countable index normal subgroup, since the image here is countable. And what this forgetful map really gives us is a one-to-one correspondence between normal subgroups in the big mapping class group containing this kernel to those normal subgroups of the ordinary mapping class group. So when the underlying surface is not the two-sphere or the plane, here the mapping class group is non-trivial, so we get lots of countable index normal subgroups. On the other hand, we also have an action on the Cantor set since it's preserved. And again, you can verify that this homomorphism is surjective, and the kernel consists of those mapping classes that fix the Cantor set pointwise. And that's exactly giving us the subgroup of pure mapping classes. And this pure mapping class group is an uncountable index normal subgroup simply because this homomorphism group is uncountable. And our main result shows that there is a dichotomy for normal subgroups in these big mapping class groups. Namely, if you take an arbitrary normal subgroup, either it lies in the pure mapping class group. In this case, it will be uncountable. I mean, having uncountable index, or it contains the kernel of the forgetful map, and in this case, it will have a countable index. In other words, among normal subgroups of uncountable index, the pure mapping class group is maximal, and among countable index normal subgroups, the kernel of the forgetful map is a minimal one. There are several direct consequences of this result. First, if we consider an arbitrary homomorphism from the big mapping class group to a countable group, then it must factor through the forgetful map to the ordinary mapping class group. And the reason is that the kernel of the homomorphism phi must has finite index, has a countable index, so it must contain the kernel of the forgetful map. So this tells us that any homomorphism to a countable group actually comes from a homomorphism from the ordinary mapping class group to that countable group. In the case where the underlying surface is the true sphere or the plane, the mapping class, the ordinary mapping class group is trivial, so the kernel is everything. So in this case, there's no non-trivial countable index normal subgroup, and the pure mapping class group is a unique proper maximal normal subgroup. This is also recently obtained by Nicolas Belamis using a different method. And a consequence of this corollary is that the homomorphism group of the Cantor set is a single group, which is a classical result. We can also use theorem 1 to compute the first homology of such big mapping class groups. And they agree with the first homology of the ordinary mapping class group. And the isomorphism is induced by the forgetful map. And the way you see this is to consider the commutator subgroup of the big mapping class group, which is normal, but you can easily verify that it's not contained in the pure mapping class group. Therefore, it must contain the kernel of the forgetful map. And then you can verify that the commutator subgroup of the big mapping class group under the map, forgetful map, correspond to the commutator subgroup of the ordinary mapping class group. So the quotients on the two sides, they agree with each other. We can also apply this to other normal subgroups of the mapping class group. For instance, we can consider the normal subgroup generated by all torsion elements. This turns out to be the entire group. So the entire big mapping class group here is generated by torsion. So just for comparison, for ordinary mapping class groups, it's known that they are generated by torsion elements. And for instance, a theorem of Korkmaz shows that you can just use two torsion elements to generate these ordinary mapping class groups. And in the conversation with Dan Marklit, he asks whether kind of similar thing happens for big mapping class groups, namely whether every big mapping class group is generated by torsion. Theorem 2 gives a partial answer since we only consider a special family of surfaces of infinite type. Actually, we can do better than theorem 2. So instead of taking all torsion elements, we can take a single torsion element and ask whether it normally generates the big mapping class group. Here, when we say an element normally generates some group, it just means that the normal closure of the element is the entire group, and the normal closure of an element is a subgroup generated by all conjugates of that element. And theorem 2 tells you that this happens for a torsion element gamma if and only if its image under the forgetful map normally generates the ordinary mapping class group. And there are lots of elements like this by a theorem of linear modules. They show that in the case where the surface is closed and has genus at least 3, a torsion element gamma normally generates the ordinary mapping class group if and only if the gamma does something complicated enough on the first homology. Namely, it's not the hyperelliptic involution. And so in this sense, most torsion element has normal closure equal to the entire mapping class group in both the ordinary case or in our big mapping class group scenario. The way we deduce theorem 2 and theorem 3 from theorem 1 are very similar. So I'll just show you how we deduce theorem 3 from theorem 1. Here we'll prove the non-trivial direction, where we assume that the image of gamma normally generates the ordinary mapping class group and show that the original torsion element normally generates the big mapping class group. So here it's natural to consider the normal closure of gamma. And the first thing that we prove is that it's not contained inside the pure mapping class group. Actually, the pure mapping class group here is torsion free. So in particular, it cannot contain the torsion element gamma. And one way to see this is to apply the Nielsen realization, which we proved in an earlier joint work with Danny Calegari and Lehman for all surfaces of infinite type. So what this means is that we can represent gamma by a periodic homeomorphism on the surface of finite type, preserving the Cantor set. Now, if gamma lies inside the pure mapping class group, it will fix the Cantor set pointwise. So in particular, it should have infinitely many fixed points. On the other hand, one can show that any periodic homeomorphism other than the identity map on the finite type surface must fix only finitely many points. And one way to get this is to consider the Lefschetz number, and you can actually bound the number of fixed points. Anyway, we deduce from here using theorem 1 that the normal closure must contain the kernel of the forgetful map. Now, to show the normal closure to be the entire big mapping class group, you just need to verify that its image under the forgetful map is the entire ordinary mapping class group. But it's easy to see that the image is exactly the normal closure of the image of gamma, and which by assumption is the entire ordinary mapping class group. So this completes the proof of theorem 3. For the remaining time, I'll try to explain some ideas that goes into the proof of the main theorem, theorem 1. And what we really need to do over here is to think about the case where we have an element that that's outside of the pure mapping class group. And what we need to show is that the smallest normal subgroup containing that element must contain the kernel of the forgetful map. In other words, we need to show that the normal closure of any element gamma outside the pure mapping class group contains this kernel. And our proof actually gives a better way to understand this kernel. We actually give a nice generating set. To describe the generating set, I need to introduce the notion of a dividing disk. Here, actually, we only consider the case where the surface S has one puncture. The closed case can be easily deduced from there. So here, let me explain the notion of dividing disk in the case where we have a torus with one puncture. So a dividing disk is a disk embedded in the surface S, so that its interior and exterior both intersect the Cantor set K in a non-trivial way, whereas the boundary of the disk is disjoint from the Cantor set K. And the basic observation is that any mapping class supported in such a dividing disk must become trivial under the forgetful map, because it's supported in the disk witnessing no homology. And the nice thing that we show is that the kernel of the forgetful map is generated by all such mapping classes supported in dividing disks. And this is a fragmentation map. Now, to achieve our goal, showing that the normal closure containing the kernel, what we need to do is to verify that every mapping class supported in the dividing disk is actually an element of the normal closure of gamma. And this is achieved by a suspension argument. So the fragmentation lemma, the proof divides into several steps. So I can just roughly explain the ideas. So what you do is that you factorize an arbitrary mapping class in the kernel of the forgetful map into mapping classes that preserve more and more structure on the surface S. So you can start out by factorizing an arbitrary mapping class into a product of finitely many mapping classes that each of them fix an arc connecting a point, the puncture, and a point in the Cantor set. Then you can further factorize an element fixing such an arc into elements that further fix some collection of arcs that cut the surface S into disks. And from there, each element that you consider would be supported in a dividing disk, and that will give you the proof. And for the remaining time, I'll explaining some details in the suspension argument, showing that an arbitrary mapping class supported in the dividing disk can be written as the product of conjugates of gamma or gamma inverse. So we start out with an element gamma that's not in the pure mapping class group. So it must display some point X in the Cantor set. Now we can choose a tiny dividing disk D surrounding the given element X, so that its image E is disjoint from D. And one nice thing about dividing disks is that they are all the same up to homeomorphisms. So we can picture the Cantor set in the dividing disk in whatever way we like. And here we picture the Cantor set in D as a sequence of Cantor subsets converging to this point X, so that we can construct a sequence of dividing subdisks D0, D1, D2, and so on, converging to X, together with a mapping class H supported in the dividing disk D, taking D0 to D1, D1 to D2, and so on. So it's almost like a dilation, and we also make it so that it preserves the Cantor set. Therefore, we can think of H as a mapping class in our big mapping class group. Remember, our goal is to show that an arbitrary mapping class supported in a dividing disk lies in the normal closure. But since dividing disks, they all look the same, up to conjugacy, we might just assume that this target mapping class G is supported in the dividing subdisk D0. Now, if we take the conjugate of G by H, that will be instead supported in D1. And if we conjugate by H squared, it will be mapping class supported in D2. And what's sweet about these homomorphism groups or big mapping class groups is that you can define this infinite product to obtain some non-trivial elements once you take these mapping classes of disjoint support. So here, this infinite product alpha G is a well-defined mapping class. And what it does is that it kind of applies a copy of G to D0, and similarly to D1, D2, and so on. And we fix the point X. Now we consider the commutator of alpha G with the starting mapping class gamma. And then parsing the commutator one way, we will see that this is a conjugate of gamma multiplied by gamma inverse. So this is an element in the normal closure. Parsing the commutator in the other way, we see that this is alpha G multiplied by a conjugate of alpha G inverse by gamma. So what beta G does is that it kind of applies a copy of alpha to each disk Di and applies a copy of G inverse to each disk EI. And it is the identity outside of these two sequences of disks. Now we need to construct one further mapping class that swaps the two disks D and E. This is the mapping class B. Its restriction on the disk D is just the starting mapping class gamma. But to get away going back from E to B, instead of taking gamma inverse, we further compose it with the dilation like mapping class H. So in this way, we take the B map takes E0 to D1, E1 to D2, and so on. And now we consider the conjugate of beta G by B. So here's an illustration. As I mentioned earlier, beta G kind of applies G or G inverse to EI, Di, and EI in kind of an alternating way when we list the disks in this sequence. And the mapping class B shifts this sequence of disks to the right by 1 unit. So the conjugate of beta G by B kind of gives you the same alternating pattern, but everything is shifted by 1 unit. So when you multiply these two elements together, everything cancels out on all these subdisks, except on D1, we just get the original copy of G. So in this way, we see that G is the product of beta G and the conjugate of beta G. But beta G is an element in the normal closure of gamma, so does the element G. So this completes the proof of the suspension lemma. I'll stop here and thank you for listening.